Okay. We are now being recorded. Do you just want to do a continuation of the study guide or anything we were working yesterday?
Yeah,
Okay.
just a continuation. If we can go a little bit faster, because I would love to really get into like week 4's material.
Saying week 4 is the one I'm having issues with.
Yeah, but I don't think it makes sense to like do week 4 and then week 3 and kind of go backwards. So
Yeah, we can kind of fly through some of these. Let me real quick open some other stuff. Let me rearrange my computer so everything's in the right place. If y'all don't have a computer that has multiple monitors, I would highly recommend investing in one.
you don't do just split screen?
No, it's just too small. You're as you keep going through the program, your eyes are gonna get more and more tired. And I also got I would invest in a nice pair of blue light glasses as well.
Okay.
That's two things to kind of save your eye. And also I have a walking pad and a whole standing desk set up so that I could because like you're gonna spend a lot of time just sitting at a computer otherwise.
Yeah, you told me that like the first time we got on a tutoring session, and I completely bought a brand new desk and walking pad, and it's been so awesome.
It's so much nicer to be able to move, and it helps you stay awake on those rough days.
Yeah, for sure.
Let's go ahead and we'll just start kind of flying through some of this, eventually try and get down to the other stuff. Okay. So know and identify oxidized and reduced forms of the molecules. This right here, this is just going to be honestly just a chunk of memorization. So the primary alcohol, so we have primary and secondary alcohols. He doesn't go a ton of detail into this, even in the book, but just knowing what they oxidize down to. That primary alcohols oxidize to aldehydes, and then the secondary alcohols oxidize to the ketones. He likes to ask questions about those things.
Your shared screen is not updating. Like you're way up by like hypertonic solutions.
Let me reshare. Is that better?
There we go. Yes, thank you.
Okay. Yeah, so we have the primary alcohols go to aldehydes. Secondary alcohols go to ketones. Aldehydes are oxidized to carboxylic acids. You can even rearrange these. What this is saying right here, carboxylic acids are reduced to aldehydes. That's just saying the opposite, because if it goes oxidizing one way to carboxylic acid, the reverse, if it's reduced, it goes back to an aldehyde. And again, the aldehydes are reduced to primary alcohols, etc. It's just like that back and forth kind of play. Not like incredibly important to know, just I know he does occasionally like to throw questions like that into everything. Let's see if I can get this to jump back.
Hey, Drake.
What's up?
I'm having trouble logging into Penji. This is Mina or Lindo.
If you have issues with Penji, contact their customer support. I literally can't do anything with Penji.
Oh, okay. You can't like let them know that we were present or something?
Contact Penji if you're having issues logging into it. Yeah.
All right. Thank you.
Okay. Other important chemical reactions should be its own thing. Okay. A lot of this has to do with just the functional groups. Really kind of annoying, but to be honest, this is just your standard memorization of that acid plus alcohol is an ester bond, acid plus sulf should be hydryl. Group is a thioester, and honestly, these won't be super important until next try in Biochem 2. Just touching on it here so you have an idea about it right now. Know and identify all of the functional groups. So, boom, functional groups. The ones that you're really going to want to know, methyl is one that we talk a lot about. Oxalate, hydroxyl, sulfide, phosphoryl. Okay, those are the, and then the amine. I think those are the main ones you want to know. Don't kill yourself memorizing these. Honestly, like I don't think he doesn't usually ask like super hard on these, but like at the end of the day, you're gonna have your time is gonna be more worth it spent studying other things than just like trying to memorize all of these right before the test. If you want to make a quick Quizlet and like practice them a couple of times, that'd be good. But those ones that I highlighted, the main ones you should focus on.
What's the difference between like a functional group and like the amino R groups? Because isn't alanine CH3 or something like that as well? But it says methyl.
Methyl. So they can be similar. So like our amino acids. So but you could even say our functional groups of the amino acids. Our carboxyl group is a functional group. Our amino group is a functional group. This R group potentially could also be one of our common functional groups. It's just kind of a functional group is referring to something that's literally going to definition. So a functional group is defined as an atom or group of atoms within a molecule that has similar chemical properties whenever it appears in various compounds. So like I think you could technically call those R groups functional groups, but they're not like the ones that are commonly found. You don't typically group those R groups with the traditional functional groups.
They're not the L isomers or whatever like that we use for the 20 L isomers for amino acids, right?
That's different. That's just talking about the actual amino acids themselves. An amino acid is made up of several functional groups. Like every single molecule is going to have functional groups, or at least one functional group. Don't go too deep down that rabbit hole. Don't worry about that.
Okay.
Just these are the ones that you want to know. Focus on these. Understand that these are the functional groups that are going to be present in a lot of atoms, and that they will be the ones with which interactions and stuff are going to be happening. Don't go much further down that rabbit hole. That is above our pay grade, and if they're not paying us for it, why would we learn it? Okay. Know the structure of amino acids, which we literally just talked about. There should be 4 things that come off of an amino acid. What are those 4 things?
Is it the carbon backbone and the R groups?
We have an R group. Then we're also going to have a carboxyl group, which is that COO minus. We have an primary amino group, which is our H3N, and then a hydrogen, or almost all of them, right? The only one that's different, I'll save that for the next question. So these guys are going to be our structure of our amino acids. Our amino group, carboxyl group, a hydrogen ion, and then our R group. That's every single amino acid is made up that way. And remembering that the center is called our alpha carbon, aka our chiral carbon center. You can tell me what chiral means.
Bonded to 4 different things.
Yeah, so it is to 4 different things. So every single amino acid has a chiral center, except for which one? There's one amino acid that does not have a chiral center.
Is it glycine?
It is glycine. Glycine, instead of having its R group, is just another hydrogen. So because it is bond to just 2 hydrogens, it does not count as a chiral center because it's not bound to 4 different things. Okay, know what is the zwitterionic structure of amino acids. So zwitterion, we'll talk about this a little bit. What is the definition of a zwitterion?
When it has both positive and negative parts? Or is it acid and base parts?
A molecule that can act as both an acid and a base. So just like our amino acids, we have that, which you can kind of look at it like it has hydrogens to donate, hydrogens to that it can accept. So kind of like that positive and that negative charge. But focus on its acid and a base. It acts as both of them. Awesome. Know why amino acids have amphoteric characteristics. We talked about amphoteric a little bit last time. Does anybody remember what amphoteric means?
Are
We mentioned it before.
amphopathic and amphoteric the same?
Where's that? Yeah, I think that may just be. Amphipathic versus. I'm not sure if they're the same. So let's stick for right now that they're different. Because one was talking about positives and negatives. This one is just saying that it has both acidic and basic characteristics. So similar. It's just kind of like thinking of like AKAs with tarions. Will also be amphoteric. I mean, they have both the acidic and the basic characteristics. It's more like vocab that's AKA. It's all saying the same thing, just different ways to say it, because saying it one way would be way too easy. Okay.
Also, I was gonna say, because I have on my notes that amphoteric, it says can act as a weak base or acid, but we just said zwitterionic or structure. So they're the same thing?
I would say yes.
Okay.
Let's go.
I think the difference is that zwitterion can act as both and amphoteric can act as either. I mean, I guess, is that the same thing though?
Let's go Google says.
No, that
An amino
that's
acid dissolves in water. The zwitterion interacts with H2O molecules, acting as both an acid and a base. But unlike simple amphoteric compounds that may only form either a cationic or anionic species, a zwitterion simultaneously has both ionic states. Okay, so it's talking about the amphoteric compound can do either. So this is saying can act as a base or an acid, depending on its situation. But this one acts as both. That's the difference between the two. Don't you love Google?
So helpful.
I do. Okay. A peptide bond. What is a peptide bond? Who can tell me the definition?
A covalent bond.
Okay, so it is a covalent bond. What else? What else do we know about peptide bonds?
They connect amino acids.
Perfect. How are those?
Condensation.
How are they formed? So they're formed through condensation reactions. What's another name for condensation reaction?
Dehydration.
Dehydration reaction. What are the products, or what are the extras of that reaction? What else gets formed besides the bond?
What else can form besides the bond?
What else gets formed during the reaction, the condensation reaction?
Water, H2O.
Water.
Sweet. What is the opposite of a condensation reaction?
Hydrolysis.
Hydrolysis, or also called hydration. Hydration, which because hydration reactions involves hydrolysis. Okay, in what direction are peptide bonds formed? For example, what parts of the structure are involved in the peptide bond? Is it the R group, the hydrogen, the carboxyl group, or the amino group?
It is the it's carboxyl and the or carbonyl, or I don't know which one that is, carboxyl carbonyl, and then it's a amine group.
Awesome. So when these start to get formed, right? Because when we string a whole bunch of these peptide bonds together, we get a primary structure. What is the name of that primary structure? What do we call primary structure?
A sequence of amino acids.
Correct. There's another name for it though. It's a
Polypeptide chain.
polypeptide chain. So once we get a whole bunch of them together, equals a polypeptide chain. And when we get down to the next chapter, a lot of this will be, we've already kind of covered it here. Okay, so when these bonds are forming, you actually get, you see your amine group is going to be what's called your N terminus, and your carboxyl group is going to be your C terminus. Polypeptide chains are produced from N terminus to C terminus. What that means is that at the very on either end of the amino acid, you're going to have your amino group, and then it connects to a carboxyl, and it has a carboxyl group on the other side, which bonds to amine group, attach a carboxyl, amine group, carboxyl, like this. Does this sort of make sense? So on the one end of a polypeptide chain, you're going to have open an amine group, and on the very end of that, so it's at the beginning of the chain. At the beginning of the chain, there's an amine group open, and at the end of the chain, there's a carboxyl group open. And if we want to continue to build this chain, another amine group is what's going to bind to the end, like so. Does that make sense?
Yes.
Okay. Now we have amino acids by their polarity. We're going to have non-polar and polar. Has anybody come up with a mnemonic or anything to help themselves remember?
I use that one video on YouTube where it's like that one tutor, he shows you how to remember it off based off your hand. So I use that. I understand it. It's pretty cool.
Do you know what that video is called by chance? Just remember.
Sarkar Tutoring Services for Biochem, and I believe it is when he's going. I believe he's going over video or lecture 4. I believe. So that should be at the very beginning. Or maybe it might be video 3, but it's right. He's like standing in a hallway.
Okay, I'm not familiar with that one. But if you're able to pinpoint exactly where that is, and you want to like, you can put a link in. You can put a link set for like a specific timestamp in videos. This honestly was just kind of straight memorization. You have glycine, alanine. Actually,
You do
let's do it this way. Glycine, alanine. What's that one?
Yeah, so glycine, alanine, proline, and then valine.
I'm gonna write the 3-letter words and
Yep.
have you guys tell me what they're supposed to be. Valine. What else is there? U is what?
Leucine. And then isoleucine. And methionine.
Sweet. And the polar. SCR, what is that one?
Serine.
Serine. THE is our threonine.
Threonine.
We have cysteine. What's special about cysteine?
Disulfide linkages.
Disulfide linkages. We talked about one example of disulfide linkages, one particular protein in the human body that requires disulfide linkages. Does anybody remember what that is, what it talks about in the book? It's to do with insulin. Insulin is one that requires those disulfide linkages in order to form. We have asparagine, and then glutamine. Very nice. Okay, now we have by their chemical groups or special elements or structures or according to their functions, such as our sulfur containing. You guys a mnemonic about sulfur containing. Does anybody remember what it is?
Yeah. So are you asking which ones are the sulfur containing ones?
There's a mnemonic or a little saying that I had talked about.
The MCs have soul.
B
Threonine, cysteine.
Yeah. So methionine, cysteine. Those are the ones that are our essential amino acids. Technically, I don't want to mention that. I don't want to confuse you guys. Actually, I will throw this one in here because this one is a little bit special. Homocysteine. Homocysteine is a little bit different in that it's not an essential amino acid for everybody. Does anybody remember what's special about homocysteine? Or who it's essential for and who it's not? see if I can find. I want to make sure that I say it right. You know, he has it in his lectures. He makes a big deal about it. So homocysteine is one of the only amino acids that it's like one of those potentially essential amino acids. It's not counted as one of the 20. So if you ask how many essential amino acids are there, you say that there's 20. Where is it?
Is there
I can find it.
is there a way that we can get your notes or no? Like, because I'm taking notes as well, but like I like how yours is like nicely typed and stuff. Is there a way we can get that too or no?
Yeah,
It was shared.
Yeah,
Oh, it was?
I'll throw it in the link again.
It's in the group me.
It wasn't in the group me, but it was in the last chat. I just shared it in
Okay.
this chat as well. Okay. The thing I remember about homocysteine, I don't remember off the top of my head which one it was, but it is one that is not essential in everyone. I think it's non-essential in, I don't know if it's in kids. Can the human body make homocysteine? Okay, so the adult human body, I'm pretty sure this is it. Do not double check this in case if he does ask this. But homocysteine is naturally made in adults, but for children. So I should say it's non-essential for adults, essential for children. What I'm saying. That's what I want to say. That means that our body can produce homocysteine by itself as an adult, but children cannot. So a child must consume homocysteine in order to have it in their diet, in order to survive, or to have it in their body to do whatever they need to do. Okay, branch chain amino acids. Does anybody remember the mnemonic? Live on a branch. We have our 3: leucine, isoleucine, and valine. Our acidic amino acids. This is acidity of as and glutes. This is our aspartate, aka aspartic acid, and glutamate, aka glutamic acid. This isn't for way later on down the road, but a good thing to know is that glutamate is the primary excitatory neurotransmitter within the central nervous system. That will get brought up a lot in future classes. Not for a while for you guys, but it's a good thing to remember now. Might as well expose you to it now. Okay, our basic amino acids. This one I don't really have a mnemonic for, but the 3 that we consider basic is lysine, arginine, and histidine.
His name's Hal. He's a nice guy, Hal.
Or even Hal is basic.
He's positive, or he's a basic person, sure.
It reminds me that was Hal. I think it's Hal from. I don't know if you guys remember this. This is from what's it called? Tool Time, like Tim's Tool Time. The show at night, maybe not. put this in the right order. Histidine, arginine, and lysine is in the right order. Al is basic. We have our amide group containing amino acids, spargine, and glutamine. This is so a lot of this again is just kind of memorization. It's really unfortunate because you don't need to know a lot of these for boards. Like the big ones you need to know eventually for boards are like the sulfur, the branch chain, acidic and basic, and then like the aromatic ring groups. But he will test pretty heavily on just questions that are like, which of the following is an amide group containing amino acid. Like he'll ask questions like that. Our hydroxyl containing are serine and threonine. I suppose that if you understand what groups these contain, then it'll be a little bit easier. It should, as ideally, it's easier to understand like their interactions that they would have with other stuff. Okay, the aromatic ring, the ring structures, it's you trip, your pal, Iron, and the ring. That is tryptophan, phenylalanine, and tyrosine. That'll be an important one to remember for boards as well if you want to make notes. Our neutral amino acids, alanine, glycine, leucine. Already talked about this one, the non-chiral. Literally the only example he gives is glycine. That's the only one we care about. Which amino acids to form disulfide bonds. Already talked about that. Okay. And that is our wonderful cysteine. I don't know if this will come up, but when it forms the bonds, they call it cysteine, like that. I don't know if he ever really mentions that or not, and I don't think he'll ask a question like that, but might as well throw it in there so you guys have that information. Come on. Okay, modification of amino acids. So a lot of the rest of this is kind of just going to be like, it's kind of just memorization type stuff. I'll go ahead and just throw this in here. So you guys can go through and look at them. They're not like, a lot of this again is just sort of memorization. I wouldn't kill yourself knowing these, but I guess I would be more importantly, I would know the definition of each of these. So like glycosylation, I would look up the definition of each of these. And glycosylation. So this controlled enzymatic modification of an organic molecule, especially a protein, by addition of a sugar molecule. So I would, is rather than having all of this extra stuff, I would literally just write addition of a sugar molecule to a protein. I would follow these up like that because you can understand what they are. like acetylation, addition of acetyl group, carboxylation, adding a carboxyl group, oxidation, losing of an electron, or it could be addition of an oxygen, hydroxylation, losing a hydroxyl group, that OH, or addition of the hydroxyl group. And equals have the addition of the metal ions. Okay. He has examples of each of these in the book, but again, it's just kind of memorize, which I don't want to. I want to get to the stuff that we're struggling with. Okay. Any questions up to this point? Pauses, breaks. Everybody good?
I'm good.
Okay. Okay. No peptide bonds, polypeptide chains, proteins. We already talked about peptide bonds. We talked about polypeptide chains, how they're formed. And then proteins we'll get into. We talked about a couple of the different proteins that we've talked that have been mentioned in the book. But honestly, these will all kind of get encompassed as we continue down through the rest of this list. So fibrous proteins. First things first, what's the main difference between fibrous proteins and globular proteins?
Fibrous proteins are they're it's collagen and keratin. They're like for structure, and they're insoluble.
There it is. Fibrous are insoluble, and globular are soluble. What does that mean? Insoluble versus soluble?
Dissolve in water or not.
Exactly. So that's why. So if we know that simple fact, we can then talk about or like think about what the function of these were going to be. So if a fibrous protein is insoluble, why would we want the fibrous proteins to be insoluble?
Because they're supposed to hold their structure, help the structure or something, right?
So if you think about it, what percentage of our body is literally just water? Like 60 to 70 something percent of our body is made up of H2O, which is just a crazy percentage of our entire structure. So if our fibrous proteins were not insoluble, literally all of our cellular structure would just dissolve into itself, and we would have no shape and no form. So that's what understanding that fibrous are insoluble will give you the rest of that it's the support to our structure. And the collagen and the keratin are the best examples of that. Okay, so globular proteins, these ones are water soluble. Best examples, myoglobin and hemoglobin. We also have our integral membrane proteins. These are the proteins embedded in the membrane. They support structures and/or functions. And sometimes they do both. So we can think of like our membrane enzymes, a lot of our receptors. We'll get a lot more into receptors and like communication and like ion channels. That's another one, ion channels. We'll get a lot more into that down the road. How those work, and a lot of this. This right here, integral proteins, receptors and ion channels. This is why a ton of people fail physiology. Okay, I'm gonna say it right now. A ton of people cheat their way through this class, and because they do not understand receptors and ion channels, they fail physiology next try. Okay. Do not skip out on understanding this stuff. You need to understand receptors and ion channels, and we'll get more into it as later on in the try. But do not think that you can get away with just kind of half-assing it through a lot of this material, because I promise you it will bite you in the butt next try. That's why physiology is a class that has a 20 to 50% fail rate in this program. Okay? Don't want to say that to scare you, but understand a lot of these concepts here in biochem come back in physiology. And if you did not understand them now, you won't understand them then, and you won't be able to apply them. And if you can't apply them, you will not do well in that class. And it will be incredibly stressful for you because you have a ton of other stuff and material going on that you're needing to review and study at the same time. Okay. Continuing. Primary, secondary, tertiary, and quaternary structure of proteins. A lot of this is going to be continued down here, but let's just quick list off what they are. Okay, the primary structure, what is it called?
Polypeptide chain.
Our polypeptide chain. What kind of bond holds it together?
Covalent.
Our covalent, aka peptide bonds. Perfect. Secondary structure, there's two secondary structures.
It's the folding. It's the alpha, beta, and the alpha helix and the beta sheet.
Beta sheets, perfect. We'll talk a little bit more about that. There's left and right-handed alpha helix, and there is parallel, anti-parallel, and mixed beta sheets. What are the primary bonds that form a secondary structure or protein?
Are they hydrogen?
Hydrogen bonds is our big one. And also this is where we'll see a lot of our cysteine bonds as well. Are those disulfide bonds? Tertiary structure. What is our tertiary structure?
Lots of, or like a couple secondary structures together.
Yep, it can be secondary structures together. This right here can be a functional protein or part of a quaternary protein. Okay. This is a big concept to understand. Not every protein has a quaternary structure, okay? There are tons of proteins that they get to tertiary and that's it. That's all they have. They're done as soon as they get to tertiary. They're a fully functioning protein and they go off and they do their jobs, okay? This again is going to be thanks to hydrogen bonding. Now, our quaternary structure, what is a quaternary structure?
A bunch of tertiary structures like hemoglobin and myoglobin, right?
Multiple tertiary structures come together and bind to form a larger functional protein with multiple functional areas. Great example of that is our hemoglobin. I don't remember if myoglobin has quaternary structure.
Yeah, I think actually that was tertiary.
Yeah, myoglobin is tertiary.
Does the primary structure, or does that have disulfide linkages in it too, or no?
No. The primary is literally the second it starts. So you have to kind of start to think of this whole thing as these steps are taking place simultaneously rather than individually. Okay. Because you think about the body's the whole body is 3D, and these processes are taking place. Like you don't wait for the entire primary structure to form before it starts to fold into a secondary structure. So the primary structure is going to start to form, right? Each of these being an amino acid in this chain. And let's say, as soon as we get to like this point right here, everything behind it is going to start forming that secondary structure as this chain continues to form. And then as that secondary structure is going to slowly start to form, and then it's going to keep building that peptide chain. And then another secondary structure starts to form, and then those secondary structures start to interact with each other as it's building off more of the peptide chain. So all of this, the primary, secondary, tertiary, and even quaternary, are occurring simultaneously. It's just we split it up to make it more understandable. Okay. So for the purposes of this class, you can think of them as happening like as stepwise, like primary happens, then secondary happens, then tertiary happens, then quaternary happens. But in reality is a little bit different than
the textbooks.
Exactly. Then the concept, or how deeply we need to know the concept right now. Okay.
The first time you'll be seeing bonding, or bonds would be in the secondary, and then tertiary has like a bunch of them, like the van der Waals and all those other ones. But in secondary is when it starts, right? The bonding, like hydrogen bonds and disulfide.
Yeah, hydrogen and disulfide bonds are occurring in secondary. Yeah. Tertiary, you're going to have those. Is primarily driven by hydrogen bonds as well. And then quaternary, we didn't add that. The quaternary bonds is going to be, I believe it's called those non-covalent forces. Stuff like van der Waals and like, I have made a thing. Let me pull it up real quick. See the very last question on this. Yeah, quaternary structure has non-covalent interactions and also possibly more disulfide bonds. So non-covalent interactions, like we mentioned, those van der Waal forces, or however you spell it. Goodness. Yeah. Good catch. Okay. No, the bonding in peptides, we just went over it, so that can go away. Secondary structure. Secondary structure of proteins. Okay, we just touched on this, but let's go a little bit further. Know the alpha helical structure of proteins. We mentioned that there's right-handed and left-handed, right? This is referring to the way that it spins. Okay, and you're going to get the question, which alpha helical structure is the most common? The answer is right-handed. Okay, you want to know that almost all, I think, possibly all, or very, very close to all of our secondary, or all of our alpha helical structures in the body are right-handed. And that's because they are more thermodynamically stable. Okay. Beta pleated sheet, we have parallel, anti-parallel, and mixed. Knowing that Parallel, these are the weakest or the least stable. Anti-parallel, I'm fairly certain antis are the most stable. These ones are the second most stable. The beta bent or the bending occurs because they call them beta bends or beta turns. And that is due to, when we're talking about the bends, do people understand what I'm saying when I talk about the beta turns or the beta bends? Do I need to explain that?
No, I'm good. I got it.
Okay. Those turns are going to happen. Happens because glycine and proline are close together. Due to the small size of glycine and the structure of proline, they like to interact and cause a beta turn. The glycine and proline, when those two are together, you can end up getting a beta turn. And they can be within like, I think he says within like around 3 peptides of each other, and still form a turn.
So each bend won't be like the same space from each other. Like you could have a really short, I don't know, peptide bond chain with 2 bends, and then it could be really long.
Yeah, you could. I mean, there's like when you're talking about proteins, like the shape of each individual one, and like when it's talking about parallel, antiparallel, and mixed, like it's not as super rigid as like you want it to be, because like in reality, there are so many different proteins. I literally just answered the next part. There's so many different proteins and so many different ways that things have to happen, and like the rules that we're learning here are the norm. But it's kind of like the English language in that the norm is like, oh, this is the normal, but there's also like 8 million exceptions to every single rule. So it's yeah, it's similar to that. Look above, you don't. Okay. Bonding and secondary structure of proteins. Look above, you donut. Bonding and tertiary structure of proteins.
What does
Look
that
above.
mean?
What type of bonds are formed?
Okay.
So it's literally just, it's exactly what we talked about right here. The covalent peptide bonds, hydrogen bonds and the disulfide bonds, primarily hydrogen bonding. Quaternary is the non-covalent interactions like the van der Waals forces.
Gotcha. Okay, thank you.
And that's exactly how he's going to ask those questions. He's like, he's going to ask what kind of bond is typically seen with a quaternary structure, and your choices are going to be covalent hydrogen, disulfide, and non-covalent interactions. Technically, disulfide as well. So non-covalent bonds. But yeah, he'll have the question worded, and the answer will most likely be non-covalent interactions or van der Waals forces. Which means essentially it's saying the exact same thing. A van der Waals force is a non-covalent interaction. Does that make sense?
Yes, thank you.
That's all of that bonding structure here. It's literally just what we had above. Also, if I write little comments and stuff like this in study guides, or if during tutoring and stuff, actually, like, it's not meant to be personal or anything against anybody. It's just like I tend to do it in a lot of my notes and materials, just so that like as I go back through it, it's just a little something silly or something funny that I'm like, oh, it just makes me laugh and puts me in a better mood. I would highly recommend doing that, putting little jokes or little things in your notes. That way when you're going back 6 weeks later and you read it, you're like, ha, I'm funny. Okay. Know what denaturation or renaturation of proteins is. Denaturation, give me a good definition for denaturation.
The unfolding of a protein due to temperature, heat, or pH. Oh, wait, temperature and heat are the same thing. Temperature, pressure, and pH.
Yeah, so you can almost say so. It's literally modifying or breaking the structure of protein. And some of the ways that we can do that are some of the agents and the factors that cause it. So let me put this right there. The agents cause denaturation of proteins have high heat, big pH changes, so really high or really low.
Detergents, was that the other one?
Detergents as well.
Sorry, I didn't mean to cut you off there.
Okay. High heat, pressure. You actually caught yourself really good. Why are high heat and pressure essentially the same thing?
Because if you have a rise or loss of one, the other one is affected. It's a direct relationship.
Exactly. Beautiful. Okay. Denaturation. Now, renaturation. It's literally just proteins going back into its original shape. So the big thing to understand about this is that proteins can, one thing is that renaturation will typically happen naturally, okay? As long as the protein itself is like the primary structure of the protein has not been interrupted or destroyed, okay? So as long as it still has those peptide bonds forming it into that chain, as soon as we put it back into into proper conditions, it's going to fold its way back and become a fully functioning protein again. You can also let me actually add a couple here. So detergents, urea, alcohols, strong acids, all those. One thing to note though is if a protein becomes fully denatured, meaning that the primary structure has been destroyed, it will not be able to renature after that once it's been fully denatured. I have another one written here on enzymatic modification. I don't quite remember what that one is, or if it was in the book or where I pulled that one from, but I have it in my stuff, my material for one reason or another. Okay. Oxygen binding properties of myoglobin and hemoglobin. Lots of words. Okay. So who wants to tell me a little bit about, start with hemoglobin and the binding of oxygen to hemoglobin?
I don't know much. Oh, you go, Christian.
I was gonna say it can bind more oxygen to hemoglobin than myoglobin because it has it's a tetramer, so it has like 4 binding spots.
Yeah. Okay, let's talk about a couple of things.
And it has
So,
a lower affinity, I believe. A lower affinity, which in my head I just think of it as like a lower affinity means it lose it quicker than it would if it was a high affinity like myoglobin, because myoglobin like is a storage of oxygen. If I'm telling you this to tell me so you can tell me if that's a right way of thinking or not. The high affinity for myoglobin is going to store it, so that's why it's a higher affinity of O2 because it just holds on to it longer. Is that right?
yeah, that sounds right.
Okay.
So when we talk about, you brought up the good word of affinity, right? Affinity is kind of like how much it likes something, and how strong it wants to hold on to it, right? So for example, hemoglobin, one of the things that it wants to hold on to is oxygen. The other one that it really holds on to a lot is carbon dioxide. I mean, I feel like he had a question like this either on a quiz or something, but he talks about carbon monoxide. Did he guys give you a quiz question about carbon monoxide by chance?
I haven't come across one, no.
Okay. Well, the ones that we really talk about, we talk about oxygen, we talk about carbon dioxide, and carbon monoxide, right? So oxygen and carbon dioxide both have a good affinity for, or hemoglobin has a good affinity for both of those. Carbon monoxide has the highest affinity with hemoglobin. Very hard to remove. If it does come up, because I know he's had questions like that in the past. I don't know if it's was particularly in this class or when it popped up, but this is why carbon monoxide poisoning. You hear a lot about that where that kills a lot of people. Carbon monoxide binds to hemoglobin and prevents oxygen transfer because it binds with such high affinity, so it will not let go. So yeah, bad stuff. And then oxygen and CO2, their affinity is going to change. This you'll talk a lot more about in physiology 1, about what sort of things change the affinity of hemoglobin to whether it wants to bind or release oxygen or bind or release carbon dioxide. We don't really get into that in this class, but that'll be next trimester. Okay, so we talk about cooperative binding. Anybody have any idea what we're referring to when we talk about cooperative binding?
Is it the cooperative binding is like the oxygen binding to the hemoglobin, and if it binds to like one side, then it's more likely to bind to the next one, and then more likely to bind to the next one, or something.
Very good, perfect. So you can almost think of it like a chain reaction. So for some reason, this is not wanting to open for me. There it goes. So when we talked about hemoglobin, right? Well, hemoglobin is a quaternary structure, and so it has 4 different parts to it. But all together, each one of these parts has a binding site for oxygen. Okay. The difference is that each of these kind of has, the shape isn't quite perfect for oxygen. The very first one is, and that's when you'll have an oxygen bind first, and as soon as that oxygen binds, you get a conformational change. You can define for me what a conformational change is.
Just a structure change?
Exactly, it's a change in the shape. So literally what it does is it causes the next hemoglobin, the next part of the hemoglobin, to slightly alter its shape to increase its affinity to oxygen. Once that second oxygen binds, the affinity of the next one increases to bind a third oxygen, and then the affinity of that last one, the configuration changes the last one to bind a fourth oxygen. And that's what cooperative binding means, okay? When we get cooperative binding, it gives us this curve. I'll open like 12 of these, nice. So with cooperative binding, we say when oxygen binds to the first hemoglobin, there is a conformational change, shape change of the next, what's the proper terminology for it? It's like the next, I believe it's called the next functional zone, I believe. Functional zone of the hemoglobin, which increases that area's affinity for oxygen. Oxygen binds the second one, the third zone changes shape, etc. And that's where we get this curve right here, an oxyhemoglobin dissociation curve. Let's see if I can get this on this one page. Okay. Don't worry too much about the shifting, but pay attention to like this red line right here. This is talking about our hemoglobin saturation. So here at the beginning, as hemoglobin, as it starts to bind, we get a higher affinity, and then as it gets completely full, we get a lower affinity. As it approaches 100%, it gets less affinity because it's 100% bound. So this is the curve that it's referring to. Just that as more oxygen binds, our curve gets steeper, meaning that it's gaining a higher and higher affinity for oxygen until it reaches that 100%. Okay. And it's asking you to compare this with the oxygen binding of myoglobin. And just like we talked about earlier, myoglobin only has a tertiary structure. So the myoglobin saturation curve, here's an even better one comparing the two. Actually, get rid of this one and put this one in. This is the difference between the two of them. Whereas hemoglobin, because you get 4 oxygens bound, versus the myoglobin only has the 1. So as soon as it binds the 1, it maxes out. And that's the difference between the two of those. Any questions about this?
Nope, I think we're good.
Sweet. And then this last part, okay, possible.
You explained that really well. Thank you.
Good.
I was gonna say the same thing. You're a great teacher.
I've had a significant amount of practice. So I started tutoring, I think, my second year of undergrad. So it's been a very long road. And then I've been doing tutoring here at Parker for about 2 years now. So I've had plenty
You're
of
like
practice.
in biochem and tutoring biochem. No.
I was in, this is technically my second try tutoring biochem. I tutored biochem for a little bit earlier on, but I just didn't love it. I just didn't have a lot of time. But now I feel a lot more confident with it since I've been doing the videos. Dr. Sarkar's book is so good, especially after studying for boards and then going back and reading his book. Like the amount of information that is in there and how concisely it's put is amazing. So one day when you go back to read it, you'll see. Okay, and so whenever we talk about in biochemistry, we always have to have opposites, right? So our positive cooperative binding, again, will be binding of one or more of the molecules to, this is like the actual definition. I'll explain it. So the binding of one or more molecules of a ligand to a multimeric receptor increases affinity for subsequent ligand molecules to bind. Literally, this is saying exactly what you said. So binding of one ligand, or so like oxygen, oxygen just went from my brain. Can't spell it.
It's a Y. You're good. I'm like, wait, what's wrong with it?
Ooh, there we go. We're getting there. Binding of one ligand, such as oxygen, to a multimeric receptor. At one point, I knew that word. Multimeric. Oh. One ligand to a multiple parts protein. So multimeric equals protein composed of several subunits. Binding one ligand to a multiple parts protein increases attraction for the next ligand. Cool beans. So if that's positive cooperative binding, what do we think is negative cooperative binding? Literally the opposite. When one ligand binds, it makes it harder for the next ligand to bind.
Is ligand? I don't know if you said this already, but is ligand just oxygen or?
Ligand, bam. It's a molecule that binds to another, usually larger molecule. So a ligand is literally like oxygen is an example of a ligand, but you can also be like CO2. It can be acetylcholine. It can be ATP. It's like any molecule or anything that binds to another molecule. Okay.
Oh, thank you.
Go ahead and write that. Ligand equals molecule that binds to another, usually larger molecule. Again, understanding. This is why definitions are so important. I'm really glad that you asked that question, because if there's ever a definition you guys don't understand, take the 30 seconds to Google it, please. Trust me, you will make your life so much easier. Okay, subunits of adult hemoglobin. I don't remember him going super deep into this. Do you guys recall? Because so hemoglobin has 2 alpha subunits and 2 beta subunits. That sound familiar at all? I don't remember him. I don't remember being in the book and really talking about it. Okay. I guess he must have talked about it at some point. And then fetal. So fetal hemoglobin has a gamma subunit. I don't know what it replaces. Let's see what it replaces.
It replaces beta.
It replaces beta? Is that a...
It should be 2 alpha, 2 gamma. Which
Christian,
he writes
I think you're going to need to step up next try and start tutoring Biochem 1.
Oh, no. No,
I'll hand that off to you. You got all the answers, my guy.
That's awesome. For the brain. That's for the brave individuals like yourself.
2 alpha, 1 beta, 1 gamma. The reason why, the big thing about the gamma is that gamma has a higher affinity for oxygen. Why do we think that newborns, that specifically fetal, so inside of the womb, why would we want them to have an even higher affinity for oxygen? Why do you think that's necessary?
Because they don't have direct access to it. They're not actually breathing in oxygen themselves.
Exactly. So if we think about it, through what are they getting their oxygen?
The fallopian tube?
Through the umbilical cord.
Okay.
He just gets his oxygen through the umbilical cord, right? And that blood does not mix. You really think of it of like, if this is the umbilical cord, and this is where then it goes into the, well, technically it's the placenta and then the umbilical cord, and then this is where it ends and goes into the baby. The way that oxygen is actually passed, technically it's at the placenta. So here's the uterine wall. Here's the placenta that's attached to it, and the cord that goes to the little baby. Ooh, nice. So the way that oxygen is actually passed is that the mother's blood vessels pass right next to it, like this. And so you have a small barrier, and then the baby's blood vessels in the placenta go here and then continue on into the umbilical cord. So literally, the reason why you have to have that gamma subunit is in order to steal oxygen away from the adult hemoglobin. Because otherwise, if the hemoglobin had the exact same affinity, and actually these hemoglobin would have higher affinity already than the baby's hemoglobin, because the baby doesn't have oxygen full, all the oxygen bound to it. So literally, it needs that gamma in order to facilitate oxygen crossing to be able to get the oxygen to survive. Really cool stuff. Okay.
Thank you for putting it into logical terms. I think it's so easy to just get caught up with memorizing, but in reality, everything there's a reason for everything.
And if you can find those reasons, which is what's really, really cool, like if you can find those real world application parts of it, it sticks so much better and you will remember things so much better. Okay, so look for that real world application. Sometimes it can be hard with subjects like biochemistry, but I promise you, like biochemistry is used all the time, and you just need to kind of mess with it and play with it a little bit and see like, okay, why are these things that important, and how can we actually apply them to real life. Sickle cell hemoglobin. Ooh, this one I don't remember. Let's see. Okay, yeah. The only thing that I have written down that I remember from sickle cell hemoglobin is from sickle cell. Sickle cell anemia or sickle cell trait. Like that. Sickle cell trait equals 1 chromosome, one of the sex chromosome. I think it's this chromosome. I don't remember if it's a sex chromosome or how which chromosome it is that passes it. 1 chromosome has the genetic defect. Sickle cell anemia equals both chromosomes have the genetic defect. Okay. With sickle cell, essentially it's a mutation in which there is a change in the shape of the subunit structure. Because there is a change to amino acid in the primary structure. So this is why it's like, what is the most important part of making sure that a protein is functional? It is that the primary structure is correct. So literally all sickle cell is, and this can answer the next question, is a glutamate amino acid is changed to valine at position 6 of the hemoglobin beta chain. Literally that one single change completely destroys hemoglobin. It makes it incredibly difficult to use. So if you have sickle cell trait, where it's one chromosome, you have you have like half sickle cell blood type, and then the other half is normal blood. And so it just makes carrying oxygen and binding oxygen that much more difficult. So literally it has that, the subunits no longer all bind oxygen. So you get reduced oxygen saturation or carrying capacity of the body. Pretty crazy, right? That one single change completely changes the shape, and it does not allow it to do its job very well. Cool stuff, though. Fun little fact to learn about this as well in other classes and talk about this. This is actually why sickle cell trait is a natural malaria deterrent. It's actually why those of African descent are more likely to carry this trait. So if those who have sickle cell trait, the malaria virus isn't able to bind to their blood and reproduce like it would in another individual without sickle cell trait. And so actually in Africa, a large percentage of the population has sickle cell trait because it's actually beneficial to survival. Cool stuff. Okay. Enzymes. How are we doing, everybody?
Great. I'm ready to learn this lecture 4.
We got through a lot. Okay. Let's talk about enzymes. Love enzymes. Here on out, whenever Dr. Sarkar mentions specific enzymes, he points them out in a PowerPoint, or they like specifically mention them in the book or something like that. Memorize the crap out of that enzyme name and what it does. Okay. Start early because there will be a lot of enzymes. What's nice is that most of them will tell you what they do by their name, but still, there's a lot of names for enzymes that we'll need to know from here on out. Okay. Define enzyme. All right, crew. What is an enzyme?
Is it just a catalyst that like can bind to a substrate?
So it acts as a catalyst. Is an enzyme a protein, a lipid? It's a protein. So it is a protein. It's produced by a living organism. Acts as a catalyst to, what's a good word for it? To
Lower activation energy or speed up reaction?
Yeah, let's say to make it more likely biochemical reactions will happen. We'll get a little bit more into activation energy and stuff later on. So what is the effect of enzymes on reaction rate? Go fast. What is the effect of enzymes on activation energy? Who can define activation energy for me?
It's the energy you need to be able to start a reaction.
Start a reaction, nice. We'll talk about getting from substrate to transition zone products. The effect of enzymes on activation energy, it decreases.
Those questions, are you just writing those questions yourself, or is that like your old study guide he gave you? Like what?
This is the study guide that he gave us for exam 1.
Yeah.
Mine doesn't have those questions.
I think if I'm not mistaken, I remember that he because he has all of his study guides available, or at least he did for me. He had all of his study guides available at the beginning. And he had it organized a little bit differently from before. So like lecture 4 was like used to be on exam 2. So this whole part was on like the exam 2 study guide that he has. I think, again, this was 6 tries ago, so that's what I remember. I'm not 100% sure if that's accurate or not. But yeah, this should, and again, like you'll all have access to this. Okay. What are the roles of cofactors and cofactors? First, let's start cofactors versus coenzymes. What time is it? Definition time. What is a cofactor, guys?
It's a metal ion.
Metal ion. Please, 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 please do not get these two mixed up. The stupid way I remember it. Does anybody remember watching the show Fear Factor?
Yes.
So the way that I remember it is to be on Fear Factor, have to be metal. Give me 1 sec. Hey. Sorry guys, living this single dad life right now.
No worries at all.
Okay. So some of the good examples of the cofactors we're going to talk about: iron, magnesium, manganese, zinc, copper, potassium, sodium. Yeah, there's one other one, but I don't remember what it was.
Sodium, and potassium, like so sodium's like in salt and stuff. So like salt's part metal, I guess. Like, is that how that works?
It's a mineral, so minerals.
Oh, okay, mineral. Okay, that makes sense.
Yeah, they're kind of grouped into the same category. And then our coenzymes, these are our larger, more complex organic molecules. Let's see if I can. Guys, with your guys' schedule, are you guys okay if we take like a 20-30 minute break so that I can feed him, and then jump back on? Is that okay?
Yeah, absolutely.
Yeah.
Yeah,
We
that's fair.
appreciate you staying diligent.
I'm gonna go ahead and stop this recording right here.